Hello and welcome. This is Computer Science Engineering 228A, Agile Hardware Design. So this is our first lecture, unfortunately remote, as requested by university due to the storm, but I look forward to meeting you all in person at a lecture on Wednesday. And hello to all those who are watching these videos online. We're happy to share this content. This is all open source, and we're really eager to kind of do our part to put things out there. So here we are in our first lecture. So what are we going to cover today? Well, number one, I'm going to try and motivate the course, right? Why are we here? Why are we talking about this? What's so exciting about the Agile movement within the hardware design community? Talk a bit about, at a high level, what does it mean to do Agile design? And then actually get into the logistics of, what it actually means to have a course, right? And so, yeah, there's plenty of time. Please stop me along the way if you have any questions. Feel free to either use Zoom chat or raise your hand on Zoom. Um, and then following today's lecture, I'll be sticking around on the Zoom call if anybody wants to have any questions to ask me. I have an impromptu office hour, so it's kind of if you want any questions about this course, how it fits in your schedule, etc. Be happy to answer those. Great. So first off, let's kind of appreciate the world we're in, right? And that is we're living in a world of very ubiquitous electronic devices, right? Where, some number of years ago, it's, oh, people might have a laptop, or eventually everybody had a smartphone. And now we're living in a world where we're kind of constantly in contact, right? For example, if you have a smartwatch, right, you are in continuous contact with an electronic device, right? In my case right now, I have a smartwatch on. I have an earbud, sorry, wrong head side, in order for me to hear the audio for this recording. Smartphone, laptop, monitor, we're drowning in electronics, right? And so a lot of electronics, it's only become more, right? The Internet of Things is coming, things in our cars, elsewhere. So there's so many electronic devices, right, at various scales. I've just listed many small embedded devices. There's also large system-side data centers, right? So we're living in a world with a lot of electronics, and they do some pretty cool stuff, especially powered by modern advances in AI. The question is, how do we go about designing these? And so it's actually becoming a real big problem. If you think about it, what are the factors at play here? Well, for much of our lives, we've been able to count on something called Moore's Law, which is this amazing empirical observation that continues to be true. And that is it due to impressive, and I mean impressive, amazing things done by those in the device manufacturing community. They continue to make transistors more and more plentiful, right? And that's possible by making basically reducing the cost per transistor quite a bit, right? So as time goes on, for the same amount of money, you can get more and more transistors, not just more and more, actually exponentially more, right? So as a result, it's not unreasonable to have billions of transistors in consumer electronics, which is, a mind-blowing number, but they do that with these, right? And so the result is you have more and more resources to build things. However, there's a challenge, right? And that is that despite making transistors more numerous and making them smaller and cheaper, they aren't really getting much more energy efficient, right? And so when it comes to building electronic devices, sometimes in order to do more, it takes more power, and that's not really okay, right? And so the solution, of course, is rather than building a general purpose processor that runs general purpose code to do your application, you instead build specialized hardware that is efficient and highly specialized to do what you want to do, right? And so of course that'll be more energy efficient, but now you need to build that specialized hardware. And so this is the world we find ourselves in right now, a world of increasing transfer resources, but also increasing specialization, right? And this is not just a small little thing, right? For example, like take a modern smartphone on the main system on chip, the SoC inside of that main chip. It's not just a processor, right? There's a number of different accelerators. There's the CPU to run what the regular software user might think about, but actually in most modern smartphones, there's actually two types of CPUs, right? There's the big and little cores, because depending on whether you need performance or efficiency, you have a choice. Of course, there's the GPU. Very often now you have an AI accelerator. You have some compute to support the cellular modem. And then that's just the ones that are easy to think about. But there's actually a lot more buried inside there. Things for accelerating cryptography for security, things for image processing, video decoding, encoding, etc. Right? And so it's a wide range of these accelerators. There's only becoming more and more. So specialization is really becoming a thing. The challenge is to build specialized hardware, you need to actually make that design. And as you get these more and more advanced transistor technologies, they get more and more expensive to design for, right? And so as a result, you kind of have two forces running into each other, right? On the one hand, you want to build more and more specialized things to have greater energy efficiency, support a wider range of applications. On the other hand, design costs are rising. And so as a result, there's things you would love to build specialized hardware for, but you can't justify the expense, right? It's just too expensive, too much effort for how small that market's going to be, right? So the result, some applications kind of lag without the optimized hardware. You're kind of unable to really make progress, right? And it's actually there's a really interesting article if you folks look it up on the Communications ACM. That's the main broad interest computer science research periodical for about a year ago, where someone basically argued that a lot of the deep learning models we see being popular today aren't necessarily magic. They're actually just successful because they're able to run well on the hardware that's available, right? And you can imagine that perhaps other machine learning technologies might have done as well or even better, but just by chance, the particular deep learning models they were considering in this article happened to do really well because it ran well on existing hardware. And now, of course, AI and deep learning is so valuable and important, we build hardware just for it. But there's a bit of a chicken and egg problem there. Which one was first, and which one kind of justified which? So we'll see. So this definitely interests specialized hardware, but the problem is expensive. And so these are kind of a crossroads, right? Where wait, we want to build more specialized designs. They're expensive. How do we handle that? Well, the solution is somehow to reduce design costs, right? And that's what this course is going to be about, is how do we figure out a way to design hardware in a way that's much more efficient, right? That we're efficient, we're talking about less human resources and less compute resources to actually generate the design. Okay, so how might we go about doing that? Well, to set that up, we're going to kind of reduce this notion we call Agile. And in this course, when I say Agile, I mean Agile in a very broad sense. In the software community, sometimes folks will talk about Agile as like a specific trademark with very, very concrete specific details. That's not quite this course. Um, so what are two things we're contrasting? Well, the prior classic way of doing things is the waterfall approach, meaning you kind of do each step one at a time, you do it completely, and you move on to the next step. Agile is kind of methodology saying, you know what? I don't know where I'm going. So how can I possibly have the exact list of steps to complete one before the next step? I don't know what the final answer is going to look like. And so the idea is instead, get some approximation of the final answer as soon as you can, and then kind of continuously improve, right? And one thing I'll be really clear about with this talk today, as well as throughout this course, is that although I'm, of course, extremely excited about Agile techniques, it's not to say there's never a point for the prior techniques. Not so much, they did things wrong before and now we're better. It's appreciating what's the context you're in and which of these methodologies makes the most sense. So on the left, for like a waterfall technique, imagine you're building a big dam, right? When you do something like pouring concrete, you can't, change your mind, right? You can't, pour a bunch of concrete, millions and millions and millions of gallons of concrete for a dam. So you know what? That was pretty good, but it'd be great if we move this entire dam 1 foot to the left, right? That's not very easy to do, right? And so guess what? A lot of class engineering disciplines are very strong in this waterfall methodology, right? You have lots of careful planning and modeling and even simulating perhaps, and you make a design, you really check your design, you really, really check your design. But once your design is, signed off and approved, and you go forward with the construction, actually, building molds and pouring concrete, you're not going to change the design, right? You're committing to that, right? But because you're doing so much work in advance, you're hopefully pretty confident in what you're doing, right? Um, so that's worked out great for a lot of large engineering tasks, right? The key thing is that in this computing world, we aren't really pouring concrete, right? We're able to kind of, rerun code. Even if the computer is working hard, for me as a human, I can sometimes, make a couple quick changes and rerun it, right? And so what's it take to just rerun it in quotes? Um, so that's what we're going to see, right? And so with the Agile approach, the idea is we don't know what the right answer is, right? And so what we're going to do is we're going to try to kind of get something going and improve it, right? And so the example I have here, of course, imagine you're an athlete where you can't know everything in advance. You have no idea what your competitor is going to be doing. You need to do your best to train and practice and prepare, but when it comes to competition, you have to kind of adapt to what they're doing, right? And so in this case, competition is the problem you're trying to solve, but the point is that you can't know everything it's going to do in advance, but by being ready to adapt and adjust to it, that can really help, right? So this slide kind of um, conceptualizes the key idea, right? Waterfall's idea of doing it step by step, one step at a time, completing it completely, and then going to the next step. Versus Agile's kind of notion of we're kind of iteratively and continuously improving, right? We're doing something going, and it's, what, that's okay, and we'll do a little better, right? And It turns out you probably do both of these things, sometimes both at the same time on projects that you've done so far in your career, right? You can imagine, for example, when it comes to writing, um, I don't know many people who can write something so good on the first draft, right? Even if you try your best with an outline, anybody's first draft for writing is usually so-so at best, right? And so the secret is well known for how to make good writing is to revise, right? And so that's the point, get a rough draft going, revise, 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 iterate. Sometimes you even need to rewrite portions of it. That happens, right? But the point is that when you look at text, it's actually pretty good. Usually it's the result of continuous improvement. And to know how to improve that text, this kind of helps to actually have the text, right? You can try to iterate the outline level, but sometimes if you see a text written out, you don't really quite know how it's all going to fit together. Cool. Okay, so uh, that was very general. Imagine this in the case of hardware, right? Where for waterfall design, you can imagine for hardware, you would, okay, design, make a design. You would specify everything. Okay, this block needs to do X, Y, and Z. This other block needs to do A, B, and C. This other block needs to do this. You go off and send those teams to implement those blocks. They write, Verilog or whatever they're writing. Then you have those teams, test things. You integrate those blocks into larger blocks, and then you try to optimize them, make sure they're meeting their, area and performance goals. Very often, in a waterfall hard design process, kind of a lot of budgeting where they're trying to guess how much time or area certain functionality is going to require, and then as a design team, it's your job to meet that goal, right? If you do a lot better than that goal, sometimes you have a lot of incentive to doing that, so sometimes it's not as efficient as it can be. But if let's say you don't meet it, you're going to hear from management, right? And so there's kind of a lot back and forth about, well, who set these goals? Is it really that reasonable? And how do you adjust them, et cetera? But you see that process, right? You go one at a time through the steps. Eventually, you get to the end where hopefully you can verify, make sure your design works, and you go through all this, right? And so you can imagine if somebody post verification says, you know what? I wish this design is something a little different in terms of how it behaves. You're going to stand there and be very frustrated at that person because you and the rest of the team, since this long process of designing, specifying, implementing, integrating, optimizing, and verifying, you can't easily make a change, right? And so if you make a change, like over here, let's say you decide, oh wait, to fix this performance problem, I need to change something on the implementations and reintegrate it and then verify it. It's actually a lot of stuff to change, right? And you find yourself having to rerun many of these steps, right? And so the insight is why not go agile? Why not embrace the notion of running through multiple steps many times? And to make this tolerable, you automate the process. So rather than having, lots of human work and very little computing work, automate this. So yeah, make a small code change, hit a couple keystrokes, hit enter, let the computer do the work, right? And so the idea is, yeah, have an initial goal for your design, implement something. It's okay if it has only a fraction of functionality you want, just get something going, see how close you are to performance targets, and then verify and repeat, right? And keep going around this loop until it's something you're pretty happy with. So maybe your first version is going to be, lacking in features, perhaps even buggy, perhaps too slow. But as you kind of keep going through it, you can really fine tune and hone in what you want. And what's good about this agile process is that sometimes you can get a much better result, right? Because you're doing this kind of feedback directed process of saying, okay, well, what functionality is missing or what performance targets are we missing? You can really kind of go in and attack those, right? Versus when you're doing this other thing, you're kind of a little bit oblivious to what's going on, right? You don't quite know how it's all going to fit together. You don't know how it's going to perform. And so it's not quite as effective, right? Now, there's sometimes reasons why you might need to do this, right? As I said, if you're building a dam, you only can really build a dam once, right? So you really make sure you get the steps right. But we argued in this case of, computer-aided design, it's easy to change the digital design, thus move on. So perhaps take this more agile methodology of kind of, continuously improving. And so you can see me draw loops a lot in this course. This is me trying to show this notion of, iteratively improving. I even use this for the logo for the course, etc. Cool. Um, cool. So as I said, Agile is kind of thing that was, popularized in software a few years ago, but turns out I've been doing this for a long time. In many cases, it's nice to have a name for it, right? And then, like I said, the goal is to appreciate that you don't really know the exact thing you're trying to build when you start, nor do you know the best way to get there, right? If you knew that, we wouldn't have this conversation. But you have some idea, and using that working idea, you can make forward progress and, like I said, evaluate yourself along the way and see how you're doing, right? And when it comes to building a hardware component, it's one thing if you're making kind of an incremental change, okay, if I have last year's processor, I'm gonna go in and, change a few things, get a little more performance. That's not so bad. But if you have a completely brand new design team, you're writing a processor from scratch or some other component from scratch, oh man, you have no idea how it's all going to fit together, right? How could you possibly know the critical path in advance, right? You wouldn't know. Or how would you have an area estimate, right? It would be hard to do, right? And so what's nice about this approach is you can kind of go through it and say, you know what, I'm going to build, a minimum viable product or MVP, as I might say in the software world, build something, analyze it and see what you need to improve and kind of continuously go through this process. And you don't mind repeatedly going through this process because you're hopefully automating a lot of this with tools, right? And as you're thinking about this, you can ask yourself questions like, you know what? In addition to just designing this component, how do I know it's right? Well, usually you do something like testing or verification, and perhaps you can change the way you design it to make it more amenable to testing and verification. These are kind of things you can ask yourself, and it's kind of easier to do with a more nimble, more agile methodology, right? And so I haven't really spent so much time talking about it, but Agile is extremely successful in software. It's so successful in software that basically we don't talk about waterfall anymore, right? Perhaps some of you are too young to remember. There's been a number of major software projects that have gone down horribly because they were trying to do a waterfall approach, right? They're trying to completely rewrite, a desktop level operating system, failed, right? And these kind of things are just too big. They're just too big of a leap, right? And they, issues that came up at the end of the project, they weren't aware of them, and by the time they came up, there was just too much to deal with them, right? So having an agile process, you can identify issues earlier on, you can address them earlier on, you can kind of keep adapting, right? It may turn out that something when you start a project you think is gonna be really scary is not so scary, and something you hadn't thought of is a real problem you design around, right? And so the sooner you get that feedback, the better you make the overall process. And so think about this in the context of hardware design. I argue the languages are actually a really big part of this, right? So if you have or ever written Verilog, it's got a lot of quirks of the language, but the truth is, if you have good Verilog, it's actually pretty resilient. There's a reason why I use this concrete analogy to describe it. It's actually, it makes high quality hardware, right? If you have Verilog that is the functionality you need, that is correct, and you verify it is correct, and you know it's correct, and it synthesizes well design tools to produce a high performance, small area design, that is valuable, right? And guess what? Companies pay millions of dollars for IP, to access someone else's Verilog for a particular block they need. Now, the problem is that once that Verilog is in that state, it's really, really nice. But if you mess with it, if you want to change it, oof, it's brittle, right? Uh, like I said, for example, you'll see that Verilog you're really excited about because it's been verified. Well, if someone goes in and changes it, you need to go re-verify it, right? Or if someone goes in and changes it, maybe it won't be as efficient when it's mapped to hardware. Maybe it won't be as small anymore, right? And so it turns out that, as I said, you really kind of take a waterfall approach with writing Verilog because it's so tedious and hard to kind of write this language, right? And so as a result, you really spend a lot of time planning and specifying and testing. And yeah, as I said, by the time you have good Verilog at the other end, it's good, right? But it took a lot of work, and you're kind of reluctant to change it, right? And so the argument for this course is, hey, embracing some new languages and some new tools, why not be more nimble? Why not be okay changing design? Make a design this way one year, and then, oh yeah, I want to change a few things, no problem. Change a few things, and yeah, it's easy. Run the tools and let them verify it again. Let them optimize it again. And so in this course, we'll use something called Chisel. That's going to kind of be a key enabler. And so I guess the next slide. No, 2 slides away. Sorry. Um, so what makes this so good, right? Hopefully, you kind of hear me repeating this thing over and over again about Agile. But really, what are we trying to do? Number one, we're trying to reduce the effort to design, right? The idea is, have a smaller team, less people, less hours, less, everything. And the reason why is we're really going to kind of focus our efforts where we need to do it, right? If you have this ability to see the end result and how close you are to it and where you're lacking, you can waste your effort. Sorry, you can spend your effort where it's needed, right? You don't need to waste it on things you think you might need, and it turns out you didn't need. Um, by really targeting this thing and having this overall ability to evaluate, you can actually sometimes get better results, right? Especially when it comes to hardware design, you can have every team optimize their block, but it turns out maybe one team wasn't able to do as well, and as a result, they're become the bottleneck. Shoot, in a waterfall, that'll be a problem, right? With Agile, you kind of see that early on. Oh wait, this is going to become a bottleneck. And you know what? We need to really, really change that block, or maybe we need to, accept that block can't be improved, in which case we can just make everything else smaller because we can't make it any faster, for example. So it's really good to kind of have that integration early. And finally, this increased predictability, right? Where with waterfall, part of why some of these software projects are so massive that failed was that you have all these teams working in isolation, and then it's kind of this, big, uh-oh moment at the end where you try to start integrating. And is it going to fit together? How long does each team take? With one team is late out of, five, that slow down the entire project, or, what happens, right? Versus when you have this agile process, right? You have components that are continuously integrated and continuously interacting, right? And if, let's say one team runs into trouble, well, their component's going to change slower, right? They're going to have fewer improvements at a slower rate. They're going to have less changes, but they should hopefully have a working version of their component. It's just not as optimized as they would like. And that's kind of the point. Is you can kind of see this happening, and you can really do this. So you don't want to delay integration. You want integration as soon as you can to start seeing these issues early. Okay, so uh, I've made a very strong technical case, hopefully, about Agile. I'm going to make a little bit more of a moral case for this slide. And you're going to see this come through lecture slides throughout the course, but I'll try and be clear where it's more opinion versus more factual, right? So um, you may hear me use the term agile in this course quite a bit. That's what this course is about. You also may hear me talk a lot about open source. Technically, these aren't the same thing. These are orthogonal concepts, right? So agile is kind of what I'm referring to as agile in this course, this notion of this rapid iteration of the design, set of techniques to do that. Open source simply just means the thing you're talking about, you can see the source code and it's freely available and usable, right? And so turns out these are two different dimensions, right? You can do agile with closed source tools and components, right? You can do everything closed source, proprietary tools, proprietary hardware design, but do it in an agile manner really fast. Or you can mix and match, right? You can have maybe some proprietary tools, some open source tools, etc., right? And what's interesting is actually there aren't a ton of cases I'm aware of open source being done purely waterfall. And the reason why is because the nature of open source of having multiple collaborators and contributors, usually, people tend to, put code out there and other folks come out there and improve it, right? So it's kind of already that revision iteration process happening, right? So it's very natural, right? It's not something that's totally new, never heard of before. It's just what's agile class. We're trying to recognize that and embrace that technique we've known works so well, right? And so, yeah, in this course, we're going to have plenty of open source things we're using. Most of the tools, actually, basically all the tools we're using are open source, and we're using open source code when possible. Um, but it's not restricted to that, right? It's just a nice enabler for this course. Um, and what's interesting is, as I mentioned, agile approaches can reduce the hardware design costs. Being able to use open source tools or components also reduces design costs. And so the result of both of those approaches reducing cost is actually really cool. It's able to it enables more people to participate in hardware design, right? Where right now it's very expensive, it's a very high barrier to entry. And hey, guess what? If we reduce these costs of these design processes, both by the methods we're using as well as the tools, hey, that can really reduce costs, right? And I think that's really exciting, right? A larger pool of designers means we're going to get much more interesting designs out there in the world, more creative designs, more better tailored to different communities' needs. As an academic, it's also a very exciting time right now. Just recently, I guess the 2018 Turing Award lecture, Patterson Hennessy, called this a golden age for computer architecture, and they're referring to this notion of, the need for specialization combined with, lots of opportunities for architectures to do really cool things, right? And so I'm excited about this agile open source process of making that community very diverse and broad with a lot of different communities, right? And so in the academic community, as I said, there's something called, for example, Google Skywater, where they are not only open sourcing the tools we've been talking about, but actually the fabrication process for some chips. And for universities, in many cases, let you even manufacture your parts for free on their chips, right? Which is pretty cool. So you can have a little small test chip or something you want to build. And so it's not a leading technology, it's 180 nanometer, but hey, it's something. So we're kind of getting out there. And I think as this becomes successful, which I'm pretty sure it will be, I won't be surprised if they continue to improve this and continue to release smaller and smaller geometries. So it's pretty exciting. Here we are, can do very fast, very nimble hardware design, and do it all with open source. Cool. Okay. So question is, you might wonder, okay, so we talked so much about improving productivity, reducing design effort. All right, when it comes time to actually building a hardware block, what is the fastest you can build a hardware block? We're trying to, what's going to be the quickest way to do it, right? Well, that's going to be a hardware block that you don't have to write, right? So if you can if you have something you need in your hardware design and it turns out that someone else already has that and you get to reuse that, that can be really impressive, right? Now, what's cool about this is this actually really makes a lot of sense. We do this all the time in software without thinking about it, right? We constantly are adding dependencies to our project or various libraries or code bases because, hey, guess what? There's common things, right? In a given programming language, you probably have some sort of vector or list type because guess what? Everybody needs a vector or list, right? And so you as a programmer can work on things on top of that, right? And so that's kind of the goal of this direction this course is taking us in the future where when you build a hardware component, you spend more time thinking about what's novel or unique to your design and less about, just building everything, right? Hopefully you can reuse a lot. And so this is already standard practice in many ways in industry. If you're building a chip, right, you go off and you try to license what they call IP, intellectual property. That is, existing components for some blocks you need. Like, if you know you need a Bluetooth controller, you can go out and get a Bluetooth controller. Or you need a USB interface. Okay, we get USB, right? So these are things you can go out and buy or, license. Um, and so for those things that are very straightforward, it actually works really well. The problem is that sometimes things aren't so straightforward, right? They aren't quite so concrete. Something like USB or Bluetooth is very concrete. There's a spec, you know exactly what the functionality needs to do. And okay, yes, this is a hardware component supports, 4 ports of USB 3. Okay, very clear. But some things are more variable, right? And so that's where reuse gets hard. And this is why I would say in general, reuse in hardware is less common than reuse in software. Is that sometimes the thing you want is really close to what you want, but not quite the thing you want, right? And as I mentioned earlier, Verilog is very brittle. You don't quite want to tweak it too much. And so if it's not quite what you want, you get stuck in this place of, shucks, I got to write one, right? And if you're writing a component, that's so much more work, right? It'd be much better if you could reuse it, right? And here it's talking about getting a component, but if you're building a design, do you care about it working? You also care about the thing you're getting also doing the right thing, right? So it's important not only to have the right functionality, but also that you're convinced it works. And so this is a challenge, right? Um, and so it's something we're hoping the methodology described in this course will make progress in this problem. So in particular, what we're talking about, how to improve, is have more flexible components, right? Where normally with something like Verilog, you have an IP block and it's, code written once. It's a single instance. Well, if your design is a little bit different, then maybe it's not quite what you need, right? Maybe you need a crossbar and you want to, change the number of ports on it, for example, or something, right? And so um, this course, we're going to be strongly advocating what we call generators. So we're talking about these all quarter, but the idea is a generator is a piece of software that generates hardware design for the case you care about, right? Now, it can't just make any hardware for anything. No, it's a specific thing, right? So it's a generator for a specific block. So you as the hardware developer are going to make these generators that solve a specific problem and build a specific block. But the fact that it's a generator rather than a single instance means there's some amount of parameterizability. It's a little bit more flexible and thus, because it's more flexible, hopefully it's more reusable, right? So you can imagine someone saying, hey, I want to get a block that has this functionality, okay, I have a Bluetooth generator, so I use the Bluetooth generator to build Bluetooth for my design. I want to support, this Bluetooth version with this interface and these other details, right? And you put those parameters in there and then it spits out the code you need, right? And so that's what we want to get to, right? And turns out people have been trying to do this for years, right? And so actually standard practice in many large hardware companies is to already do this, right? They write generators where um, for things like, a network on chip is a good example. It's a very kind of regular standard process. They might write a generator in something like Python or Java or Perl, and that thing spits out pieces of Verilog stitched together that make the thing you want, right? And that works, but we're going to cover in this course how we can build generators much more clean with language called Chisel. But how we implement this generator, there's some nice things you can do with them, right? For example, if they're open source, you can do some cool things where sometimes there's a generator you want, but it's proprietary, so you can't use it. Well, if it's open source, that of course solves it. But what's also cool is if something is open source, um, sorry, so if something's a generator, it's more flexible, right? So normally the challenge of open source is you need to have this kind of perfect mix between having something people care about and find useful, and have enough of the community to motivate building a component, and then enough energy to actually build a component, right? So it's kind of these two things. And so it's something that's really, really commonly used, and there's a lot of people that care about it, and it exists. You can kind of see these two things having this nice feedback loop of, okay, people care about this, and it exists. We're going to keep improving, making it better. But sometimes The number of people who want to use it's too small, right? In the case of hardware components, where let's say hypothetically for networks, okay, there's people who want an 8-port network, people want a 9-port network, people want a 10-port network. Those are different communities. It's kind of fragmented. Now, what if they all wanted a network generator? Now things get pulled together. So the flexibility of generators allows you to be have a single code base, a single generator support a larger community, and a larger community perhaps gives more motivation, more incentive to actually make these codes, right? So this is kind of this fun thing where hopefully between generators plus open source, we can build some really cool things for a community, right? And so the key thing to think about generators is think of their step design flow, where normally right now you think about producing Verilog or something, and then we hand it off to the tools, and tools go ahead about doing synthesizing it, mapping it, placing it, routing, etc. We're still another step before that, which is generation, where we have some higher level description of what we're doing. We're going to generate RTL, Verilog, and then pass off the tools. So really, you're just writing programs that happen to generate hardware. And it's not, like I said, it's not doing arbitrary inference or anything. It's controlled cases, but just a handful of parameters can really make things more useful sometimes. Okay, so maybe I'll pause here. I've been talking for quite a bit, see if there's any questions so far from the course. We're going to get a little bit more concrete in just a second. Okay, so I mentioned a second ago in passing this language Chisel. So what is it? So Chisel stands for, it's an acronym, for constructing hardware in a Scala embedded language. The thing I would think about it is it's a really nice, clean language, and it's kind of its best feature is it makes it really easy to write generators. We described how you could write generators by taking a language like Python, and then writing a lot of code flows to stitch together pieces of Verilog. That's just string manipulation, right? And so you can imagine that's very error prone and kind of not very robust, doesn't really have good type information, that kind of stuff. There's a lot of reasons why it doesn't work well. With Chisel's best feature is that it's a unified single language for writing generators. It also makes hardware. So you can do it in a way that's much more natural and clean. In terms of what the actual details of the language, technically it's not its own language. Technically they call domain-specific language. As you know, it's a language specialized for embedded in Scala. So there's a language called Scala, which maybe you haven't come across yet. It's built on top of Java. So, many layers we're talking of abstraction here. But the key thing is you're writing Chisel in this course, which is technically Scala, and it runs on a JVM. So JVM is the thing that runs Java. So from the outside, it's not too different. What do the language features make it so nice? Well, from Scala, it has not only nice object-oriented functionalities, it also has functional programming. And if you haven't seen functional programming before, don't worry, we are going to cover it in this course. And so it's pretty cool. So these two things combined make Scala a pretty fun language, and that's part of why the Chisel creators were excited about it. They also liked the language had support for making its own embedded languages. Those features combined, is why they chose to make Chisel in Scala. And this has been pretty good. What's also interesting is that Chisel, look at the papers, it kind of started around 2010. It's the first of a new generation of languages, right? And so around the time when it was made, there of course been quite a few hardware languages made, both industrial, academic, hobbyist, etc. But in terms of any of those having any significant adoption, it was kind of a quiet lull, where there was, Verilog had a big push. System Verilog had just come out. It was pretty cool. VHDL had always been around, of course. But there wasn't really that much work being made in new languages, and as the Chisel kind of came along and it took advantage of the language of Scala, which at that time was pretty new, and actually really kind of pushed things forward. Since then, there's been a huge flurry of languages from hobbyists and academics at first, and actually now companies. So a variety of companies, Intel, Google, etc. Basically take any major company that has hardware engineers, they probably have some team now working on their own new hardware design language. And a lot of these hardware design languages are high, including features those companies find exciting, as well as trying to incorporate features that came from languages like Chisel. And so Chisel is kind of a nice pioneer in that sense. So normally I would try and tell you Chisel's the future. I think it's really promising. I can't promise you everything will be written in Chisel in 10 years. I can't break that promise because nobody can. What I can tell you is you can learn some really cool stuff at Chisel. You can do really cool stuff in Chisel today. And a lot of stuff you're going to learn in Chisel will be translated to other languages, especially the ones that are coming out, following up on it because they're taking functionality and features from Chisel. So that's a pitch to Chisel. In terms of how's it been used, its most well-known proprietor, so to speak, is this company called Sci-Fi. They're a company that makes system on chips. They're now a multi-billion-dollar company. Um, and part of what made that company possible is, well, where's it going to come from? Their key feature as a startup was they could make chips much cheaper than anybody else could, right? And the reason why they could do that is they could design them cheaper than anybody else could. And well, how could they design cheaper than anybody else could? They were built on Chisel. So they had this agile approach. They had Chisel. They will build chips a lot quicker and a lot cheaper than companies could. And there's one thing where you could build one chip quick, one design for one customer cheaply. They're able to do 50 designs for 50 customers cheaply, in part because they were able to amortize the creation of generators internally and reuse that same generator across multiple projects, right? When their competitors would have to spend time, rebuilding units for each design, each customer, they instead could reuse the same generator and parameterize it and go, right? So that's one of their key advantages. And it's interesting when you fully imbibe this methodology, right? Where whatever is not automated becomes the bottleneck. So, for example, when I started building all these different designs for different customers with parameters, one of the early challenges I ran into was kind of funny is actually documentation, where just because you put parameters in design and generate a design, even test a design, the customer wants documentation about what did you build them, right? And so it actually had to automate the generation of the PDF documentation for that example, what address has what controls for which things in the chip and that sort of thing. And so it kind of shows you the benefit of this, very agile and rapid generative approach, right? And so this is a Chisel kind of a key enabler. So Sci-Fi would say it's the prime contributor and user to this language. Uh, Other companies have used it to some extent. So IBM, Intel, and Google have all had teams look into it or even contribute back the open source project for it. I would say as of 2023, the best of my knowledge, a lot of those people have been poached away from those companies and pulled into Sci-Fi. So I would say, best of my knowledge, in 2023, most Chisel users are either uh, academics, at Sci-Fi, or hobbyists, which that's fine. I still it's a pretty exciting language. It's a pretty exciting roadmap going forward. Um, like I said, so we're mostly focused on Chisel in this course, but it's built on Scala. So what's cool about Scala? Scala is a pretty fun language. It runs on a JVM, means it runs a lot of places. It has both object-oriented functional programming in it. If you haven't had a chance to write this language, it's pretty fun. It has static types, but it has inference. So it's nice as a programmer, you don't always type everything. It actually can infer that in a lot of cases. When it can't, the compiler is going to warn you, oh, no, 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 I can't do that. And these types are good because kind of the mantra for Scala is really to try and build a language where if it compiles, it's going to be correct, it's going to run correctly. And if there's anything that can catch a compile time, they're going to try and catch it. So very aggressive, type checking and other kinds of error checking to try and prevent all sorts of errors. And this is the argument made by, I guess, a lot of typed functional languages, but hey, Scala is one of them actually widely used. So Scala's largest industrial users, of course, places like Twitter and Databricks. And yeah, it's a pretty cool language. It also is a nice language. It's kind of fun to play with. You can just write a couple lines at a time in the REPL in an interpreter. In the case of this course, we actually use it inside Jupyter notebooks. And so Almond is a technology to get Scala to run inside Notebook, but for the most part, you don't need to worry about that. In this course, we're providing Jupyter notebooks, and you can just modify code snippets inside there, and you're off and going. Cool. Um, in terms of uh, how this all fits together, you can be kind of repeating several things throughout the course. So I kind of made the slide to kind of graphically show you these things we keep repeating over and over again. These are things I think are kind of the key meta things to learn from this course. And yeah, the lectures, the assignments, the whole point of the course gets things clear, right? So number one is one, the top left, close the loop. Like I said, I keep drawing these agile processes as loops, and they're kind of reminding us this iterative agile improvement. That's the point of the course, right? As soon as you can, when you're doing a project, find a way to get to the end metrics, right? Doesn't mean you're gonna be optimized, doesn't mean you're gonna be good in those end metrics, but find a way to see the whole thing, right? If you're trying to write a paper, do whatever it takes to write the first draft, even if it's really ugly and you promise yourself you're gonna rewrite it, that's okay, just so you can see how it looks, right? Or in case of the hardware design, get some functionality implemented, going through the tools, and make sure all the tools work. You can pass designs from another and automate it, right? So that way you aren't constantly um, manually touching things. A lot of classic design groups have this, notion of freezing certain parts of the design, then you can't touch it anymore, and so teams can go into manually fix things. And no, 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 don't manually fix things. use tools whenever and however possible and automate things. And so closed loop's the first step, right? Getting your design to go through the entire tool flow, right? Synthesis, place, route, simulation, etc. Whatever you're trying to do, make sure you have the automation so you can see the end result. But let's say, for example, you're building a hardware component, right? And you feel like you need to make it go faster. Well, you know how much faster it could go, or if it's necessary, until you know what it costs, right? So it's really important to close that loop. The second point, design for reuse, right? You can imagine you're talking about generators, right? The whole point is we want to be very productive with our agile process. And so, yeah, let's figure out a way to build these very flexible parameterized generators to make them really easy to reuse. And that way we can spend less time writing the same thing everyone else did and spend more time writing what's unique to our design. Third, get some leverage, right? Make the tools do the work. And so a lot of times, I think people sometimes forget just how capable modern computers are, right? And so the point is, hey, we have, these systems capable of doing billions of operations per second, just sitting here waiting for our next command. Let's put them to work, right? So um, a lot of things people might try and do manually because they don't trust the tools. In this course, we really want you to embrace automation, embrace making the tools do things. And sometimes, guess what? Sometimes the tools aren't going to do it. We say that, and then it doesn't do a good job. And so it's important to understand what the tools can and can't do, and work with that, right? So sometimes it might be a case where it's optimization where you know it needs to be done. You close the loop, so you know the final result. You know the optimization is not being done. So a lot of designers at that point will be, you know what? Heck, I'll just write optimization myself. And you can do that, but now your design is more complicated. You mainly need optimization. It would be better if instead you can look at your design, working with tools, maybe getting some verbose information from them to figure out why they did not perform optimization you hope they did. Sometimes you might find that it's as simple as changing your code expression just to get it the right way, and all of a sudden now the tools can optimize your design for you. And great, that's an optimization you do manually, right? There's a lot of optimizations you do in hardware that tools are capable of doing for quite some time, and if they can't do it, it's because you either didn't ask them to, or something about your design for preventing optimization. But if you understand what they can and can't do, we can hopefully go in and make the automation do it. And this is really important, right? You can see these things are all about this agile process of, we're trying to reuse components, we're trying to make the tools do a lot of work, trying to close the loop, a lot of automation, a lot of reuse. And the fourth one, design for readability. Throughout this course, you can see me talk about code snippets. And yeah, I'll talk about some choices you might make when making code, where you may have various alternatives. Okay, well, I could write it this way or this other way. It may turn out when it comes to the actual hardware, they're equivalent, but maybe you might choose one over the other because it's much easier to actually read or for other people to understand what it's doing. Cool. Okay. All right. Well, then I think that might be my last slide of the motivation. Oh, well, here's the text we just discussed. And so I'll leave up here just briefly, but we talked about 4Ds from memory. Right? And so you can see these kind of various things, right? Closing the loop. Just really want to get iterative improvement. In order to iterative improvement, you need to get as close as you can to the final thing and then keep making it better till we get there, right? If you're able to reuse things, it doesn't just save effort for you, it also helps you reduce errors, right? Where if you keep testing and banging on this component and you keep reusing it, hopefully it's pretty low on bugs or bug free, in which case that's going to be better, right? Like I said, anytime you have a time in design process where you think, oh my gosh, I don't want to do this, it's going to be so much work, that should be a warning to you or an indicator to you that, oh my gosh, that's something I should be automating. It's very repetitive. As a human, I don't want to do it. Automate that, right? Um, and then finally, readability, right? And so we can document things, which is good, but also we can figure out how we write code in a way that makes it really clear what we're doing. So that way others that come in there can work better with it. And, you've probably heard this before that, code is often read much more times than it's written. And so it's really good to get readability right. Okay. So maybe I'll pause here for any more questions on the overall course themes, and I'll get into the logistics in just a second. Okay, well, for the logistics, perhaps you saw the course announcements. The way I think of it, there's like three potential skill areas that are relevant to this course. There's hardware design, writing things like Verilog or VHDL. There's computer architecture, and there's advanced programming skills. And if you have experience in all three, that's great. kudos. Um, Not everybody has experience in all three. That's a pretty wide skill set, right? And so uh, I think having experience in two of them is good. If you only have experience in one, but you want to learn, I want to work with you, right? I especially want to encourage folks that are software strong, that are less known and sure about hardware, but kind of curious about it. Um, I love prior offerings of this course. This is the third time I've had this course. Prior offerings of this course, I've had wonderful experience with students that have had really strong software experiences, kind of bringing their expertise to the course. We actually had one student who was, formerly a professional Scala programmer and had some great commentary, and so it was really helpful. And so I would love to have a diverse course in terms of people's prior experience backgrounds, and that'd be great to support. And so what's cool about this is a grad course, right? We're not trying to be super grueling and have lots of hard exams. No, we're trying to learn this really cool, new, fun stuff in the way I think this makes the most sense. So this course is kind of a very much a coding and talking to people, kind of interacting kind of course, rather than a very competitive exam grade kind of course. Um, if you have any questions about this, please feel free to talk to me. As I said, I'll be having office hours immediately following today's lecture on a Zoom call, or you can reach out to me some other ways via email or whatnot. Um, but I really do want to kind of broaden these in this course, right? So officially, this is listed as a grad course, but every offering so far has had undergrads in it. I want to keep that going. There's room, so let's get as many undergrads as we can. And I think this material is appropriate for advanced undergrads. So yeah, please consider this course. Um, Here's how he's putting it on. Well, you heard me talking for the last 45 minutes. My name is, I said this earlier, I'm sorry, Professor Scott Beamer. So I'm an assistant professor here in the CSE department. And my main interests are in things like computer architecture, open source hardware design, and agile designs, and graph processing. Yeah, so my research tends to do a lot of things where we think a lot about how do hardware and software interact and how do we make the two work better together. And so in this case, it's really think of it as writing software to make better hardware. Is kind of think about this course in some ways, right? And so that's very much on brand of what we do in my group. We had the pleasure of having Yuan Peng Liao as one of our TAs. He's experienced the material. He does chisel for a living, so to speak, as a grad student for a couple of years now, so he's plenty of experience with this. Um, and so we're lucky to have him as a TA. And so the two of us are excited to teach this course. We'll be scheduled office hours this week, but except for today, I'll be on this call immediately following lecture. If you have any questions, if that doesn't work for you, please reach out. We'll find another time. Uh, Great. Okay. And so then in terms of what's this course, as I said, this is an elective grad course, right? This is not a required course. This is not a heavy hitter. And so I really enjoyed creating this course, and especially from also the contributions of prior TAs making this course better to really make this kind of a fun thing to kind of play around with, right? And so in terms of what the course is going to be, the main activities are lecture, you're in it 3 times per week. Um, there's going to be labs, homework, and then a project, right? And so the way I think of this course is there's kind of two portions. There's what I call the structured portion, which is the first 2/3, 3/4 of the quarter, where we're going to have, pretty good, regular structure, right? We're going to have, lectures that cover very concrete skills, and you're going to take those concrete skills and you're going to apply them, right? And so normally the way we do is we have a lab and a homework, one lab, one homework per week. The labs usually are very short, just a chance for you to kind of try out some functionality in language, like a couple lines at a time. And then the homework's usually a much bigger kind of integrated task. And so you do that for the first 6, 7 weeks. And by the end of that portion, you're going to feel hopefully pretty comfortable with Chisel and a lot of things we've been talking about. So then the final 6 weeks of the course, you're going to do a project, right? And the project, is something of your choosing. I recommend doing it in pairs. Actually, we encourage pairs, but not technically required. And yeah, it's kind of fun. You go out and apply what you learn, make your own generator, and learn a lot about projects in general, about how to kind of manage it and iterate and improve. And so this is a structure we've done now for 2 prior offerings of this course, and we're happy to do it again for a third time. But we're going to keep adjusting this. So just to give a bit of background on this course, so it's originally CSE 293, so occasionally you may hear me or see some documentation call it that. That's the number for a special topics course in our department. This course has gone so well the last 2 times, I successfully petitioned to make this a regular course, and so it's now in the catalog as 228A, so it's a regular course, and that's what I'm really excited about that. So we're happy to keep offering this over and over again and keep improving it. Um, so we're excited. Excuse me. And so yeah, so here we are. We're going to more detail on all 4 of these components. You can see In terms of the grade, the percentages on the lower left are, um, all these things are primarily code-based, right? There's no exams. So this course is really just kind of about learning about Agile hardware design and getting into it. Okay. In terms of lectures, let's hope this is the only remote lecture this quarter. Right now it's not raining, so that's a good sign. So yeah, I will be in Engineering 2, 194. It's a nice room. Uh, I will be recording the lectures and putting them on YouTube. So like I said, I've done some past offers, happy to do it again, put it out there for the broader internet. If you get impatient in this course, you probably can peek at some lectures from prior offerings if you want to go see what's coming. But I'll be happy to, of course, do them again in person. Um, so the recording is really kind of intended to kind of capture the material for the internet. And says the YouTube recordings are going to be just me. Right now, I'm alone in my office, so there's no worry about who's being captured. When I'm in the lecture hall, I'm going to aim the camera at myself, so that way it's not going to capture anybody's image. And then the microphone I'm using, I did some experiments. As far as I can tell, it's like voice activated, and it should not capture people talking to me unless you're like right in my face. But I guess there's a possibility it might be a faint recording. We'll see. Um, that's going to be the recordings that go on YouTube. We are going to use lecture capture in the actual room, which normally goes to the internal Santa Cruz only, user system. Of course, that's not going to work today. That's why I'm using a Zoom recording because I'm not in the lecture hall. But when we're in person, that's what we'll be using. Okay, logistics aside, let's get to the fun stuff. For example, I don't know if you've noticed, these lecture slides are a Jupyter notebook. And so the reason why I did that today isn't really showed at the full capability of that, but in the future, it'll be more apparent. There's code snippets, right? And so you can go ahead and run Chisel, Scala directly in these notebooks, and all these slides are open source. And so what's fun about that is you as a student can go ahead and go on GitHub and uh, get these files, and you can play with it while I'm talking. So I might tweak the code a little bit and talk about it, and you say, what if I change the code in this way? What happens? You can just run it yourself, right? And so it's pretty fun. And so we have Jupyter for both the lecture slides, which you're seeing today, as well as the labs. They're both going to be in Jupyter. And when running Jupyter, you may be worried about, oh my gosh, I don't want to have to install a bunch of stuff. If installing Jupyter seems scary, no worries. There's a link in these GitHub repos to launch what's called Binder. It's a web service that'll go ahead and run Jupyter in the cloud for you. And so it's pretty cool. So you can just, from your browser, launch your own session, and you can see the same sites I'm going to be lecturing from. I always kind of make sure to push whatever I'm going to be lecturing that day. So maybe wait to pull until right, at the beginning of the lecture. You can go ahead and play the same content. If you want, maybe your style is to, fork the repo, and then you can go ahead and take notes inline, right, for yourself. Feel free, or modify the code. So it's kind of fun. We can make this more interactive. You can see this is kind of the fun part of this course, is we're able to kind of just do things maybe a little differently to make sense, which makes more fun. The first time I taught this course was actually during the pandemic, and it was like, oh wait, a bunch of students sitting on laptops. That's a feature rather than a bug, right? Normally we don't like remote instruction, but in this case, it was a feature because everyone now has a computer, and so they all could, write and run code at the same time. So that's why it was kind of fun to have the Jupyter notebooks. And so, yeah, when we're back in person, if folks want to bring their laptops to lecture and then, modify code them in the room type of way, I will not be offended, right? That'll be kind of more fun. Um, cool. In terms of the labs, like I said, they're also going to be in Jupyter. So the point of these labs is to really kind of a focus point. So we might have an idea, okay, here's this one API feature, this one language feature. So we try to distill it down to a handful of lines per solution, right? We're talking, maybe 5 lines the longest, but hopefully not too much longer than that. And you can kind of see it working in very controlled settings. You can kind of see, okay, here's how this function language works. Here's how this API feature works. Labs, you can work with your colleagues. You can collaborate, no problem. And then you can go ahead and submit it. There's a way to do it with Gradescope. And then the timeline for getting the auto grading feedback is not quite as fast as I would like. It says immediate here. Let's be honest, it's minutes. But you hopefully can know the result well before the deadline. So if you would like to, I got something wrong, go ahead and fix it and resubmit, and then get a perfect score in the lab, and then go on to the homework with confidence. You did the lab, right? And then our advice is do these labs early, right? We're trying to post them kind of when it makes sense, and then based on the content, you can hopefully get it done, in an hour or maybe a few hours if it's a longer lab, and then you're ready to move on to homework, right? Um, okay, so then the homework, of course, you're gonna actually need to work on larger design instances, and so these are a little bit too big for Jupyter. It's not quite so practical to fit these in Jupyter, and so you're gonna be using however you prefer to write code. Now, I should put this on the slide. Maybe I'll revise it afterwards. I want to strongly, strongly, strongly encourage folks to use an IDE or something like it. So I'm one of those old timers that loves, my simple plain text editor, and I've done a lot of code in my career that way. When it comes to writing Scala and Chisel, you really get a lot of benefit from an IDE. And so actually, when I write Scala and Chisel, I use something called IntelliJ, which we links to on our homepage. But if you don't like IntelliJ, a lot of folks, for example, like VS Code. That's great. There's a way to install something called Scala Metals, which gives you a lot of IDE-like functionalities for Scala within VS Code. So that's worth doing. And if you're like a Vim person, you can also run Scala Metals with Vim, and you can still get the IDE features. So why do I think IDE features are so important? It makes it more productive, right? Here I'm talking about make the tools do the work. Yeah, make the tools do the work. And so, for example, if you're not sure about, the name of the API function you're trying to call, code completion really helps, right? Or sometimes you're writing something you aren't sure how it's implemented, being able to highlight something and right click and say, go to implementation really helps, right? And so, or if it gives you a warning that this line is not going to compile right before you even try to compile it intentionally, also helps, right? So these are all things I think are great. So use the tools, right? Make the tools do the work. And the homework, you're also going to be submitting via Gradescope. We're going to give you some test cases, and you can run those locally. However, it's not the full suite of test cases you're used for grading, so you may want to run some of your own tests to make sure you're, extra robust about that. In terms of, understanding things come up in the real world, and sometimes coding takes longer than expected, our policy for lateness is what we call slip days. We're going to give you 3 slip days where you can choose how you want to use them, right? So maybe you don't use them all, and then all of a sudden, the fourth assignment, you have a hard time and you need to use 2 of them. Fine, you can turn in 2 days late, no penalty, right? Um, they are integer, right? So you can't say, I want to use 0.25 slip days in this assignment and 0.5 this other one. So no, you can use them in integer amounts, but yeah, how you choose to use them or not use them, up to you. There's a little bit of flexibility to kind of accommodate that. Anything else more comes up, please reach out to me, the instructor, right? I mean, this is an elective grad course. We aren't trying to be super grueling here. Um, so the point of labs is to kind of get you exposed to the functionalities of the language. The point of homeworks is to actually start doing some real design. And the point of the project is to do some open-ended design, right? Give a chance for you to actually do things um, what you're hoping to do, right? And so uh, it's a pretty cool thing to do. And so in terms of how it all fits together, um, you can figure this out as we kind of go through it. But the main thing is, yeah, you're going to propose a project. You have weeks to, you don't have to worry about it quite today. Um, you're going to have a partner and you kind of go through the process, right? You're going to propose an idea, you're going to get feedback from the staff on it. You're going to code stuff up, get something running, close that loop, and then I actually have a chance to optimize and extend it and improve it, right? And then as part of the project, you're not only going to be producing code, you're also going to present what you did to your classmates. Um, we encourage, but it's of course not required, the students also open source their projects. That way, others in the world internet can see it. So I've linked the first offerings course projects. I need to go find second offerings and link those as well. But yeah, it's kind of fun. You can see what your prior classmates have done. And so it's pretty fun. I think it's a lot of students kind of, it's a very fun kind of capstone experience to what we're doing. And it's also come up to you, right? You can kind of do, if you're perhaps very busy with other courses, do a more medium-sized project. If this is really exciting to you, maybe you can do a really big project, right? Um, cool. And so in terms of resources for this course, the main way to try to get information out there is on the public website, right? Which you may have already seen. I put as much on there as I can. Basically, the only thing that's not on there is anything involving your names, grades, and that kind of stuff, right? But yeah, a lot of stuff about the lectures, links to these various repos we keep talking about. I want to make it all out there and open as I can, right? This course is built open source. I'm happy to kind of contribute back to it. And so that's all out there. We do have a course Canvas site. It's for the students enrolled in this course. You can see things for how to submit on Gradescope. For communicating, if you want to ask questions or help each other, we have a course Slack. There's a link to that to sign up on the Canvas website. Um, And in the Agile process, we're kind of continuously upgrading both these web pages. But now in our third offering, we have a pretty good sense of the content for both. So I don't think there'll be too many radical changes, but we always will find out. Cool. And then to close, I kind of wanted to go through what you're going to learn, right? So you've probably got a sense of some whole Agile methodology, something about Chisel. Well, I'm breaking the learning objectives into two types, right? There's the concrete objectives, the things that are very clear, measurable skills, things like, hey, I can go build a hardware component in Chisel, or more generally, design a hardware generator that allows for parameterization and customizing for something, as well as just more familiarity with design, right? Understanding how to kind of put together a tool flow, continuous integration to CI, do how to do code reviews, how to verify, these things we kind of talk about. These are very concrete skills, which if you're in a hardware community, that'd be great. But I mean, these aren't only hardware, right? Things like design takes the last one, right? That's kind of a much more broad thing. And especially these meta skills, the next slide, these are not restricted to hardware. These aren't restricted only to people doing that kind of stuff. Right? For example, this agile philosophy just embrace this notion of continuous improvement, continuously revising, continuously making things better. From the project, you hopefully have an idea of seeing the process of having an idea and taking it from proposal to implementation and see how it happens and how it turns into a full release. And also just recognizing where it makes sense to apply Agile. Like I said in the beginning of this talk, even though I'm really pro Agile, it's not to say that waterfall never was a place, right? And so it's understanding how the context of something makes sense and what design methodology makes sense for that context, right? And I argue with things like Chisel, we can embrace a much more fluid Agile approach because it makes sense. But without Chisel, for stuff with Verilog, it's kind of like pouring concrete. In which case, you are going to want to have a more waterfall-like process. And with that, I'm going to go ahead and close. I think we're a minute or two over. I'm sorry for going over. Um, I'll stay online for any questions. If there's no class-wide questions, I'll stop the recording, but I'll still be on here for the impromptu office hours.